So very good morning to one and all. So in the previous lectures, we have discussed about the different probes which are used for oscilloscopes and attenuators for the oscilloscopes and the different specifications of the standard specifications of the CRO. So in today's lecture, we will see the digital storage oscilloscope. Okay, the from the last lectures we are also discussed about storage oscilloscope. It is like an analog storage oscilloscope. Okay, so by using some different display targets and flood guns, we can use the storage oscilloscope. Okay, so whereas coming to digital storage oscilloscope. So whereas in digital storage oscilloscope, we can use the first conversion of the signal. Analog signal will be converted into the digital form, and that digital form of the signal will be stored in a memory. Okay, so when the stored memory, when we store the memory, so we can retrieve anytime. Okay, for our convenience, we have to retrieve anytime. So and that retrieve of the signal is applied to the CRT deflection plates. So first of all, we will convert the applied signal into digital form, and that digital form of the signal will be stored in the memory. We will store in the memory. By storing that signal in the memory, we can access at any time. We can access that signal at any time, and we can display on the CRT screen. So whenever we require. Okay, so that is the main benefit, main advantage of this digital storage oscilloscope. Okay, so this figure shows the block diagram of basic digital storage oscilloscope. So it is only used for a single input. Okay, we have multiple inputs. We can also use the multiple inputs, or we can say it is multiple trace. Okay, so at a time we can apply 4 input signals, and that input signals are stored in the memory, and we can read out at any time. Okay, this figure will shows the single input signal that is applied, and that single input signal is first it will be converted into the digital form. Generally, the input which are applied for the oscilloscope are the analog form of the signal. So analog signals. Okay, and those analog signals are converted into the digital form by using A to D converters. Okay, so after that, the converted signals will be stored in the memory. Okay, so here we have a memory. So first of all, input signal is applied to amplifier and attenuator here. Okay, that amplifier signal, the amplifier will convert the applied input signal, and it will be amplifies the strength of the signal, and it is given to the digitizer. Okay, and the same signal is applied to the trigger. So that is for the generation of the x-axis. Okay, so time-based generator. So from the trigger, it will apply to the time-based generator, and for the time-based generator, we have a clock. Okay, and by the time-based generator, the signal is applied to the horizontal amplifier. So time-based generator will produce as the sawtooth waveform. Okay, that signal is applied to the horizontal deflection plates. So whereas in the amplifier of the amplified output is applied to the digitizer. So digitizer is a analog to digital converter, ADC. It is an ADC. So here the ADC will be converts analog signal in digital form, and that digitized signal will be stored in the memory. So here we are using some memory devices, memory storage devices. Okay, so after storing the signal, after storing the signal in the memory device, so whenever we have to display, whenever we have to apply, or we have to display the input signals, So whenever you require to display the input signals, the signals will be retrieved from the memory, and those signals are applied to the CRT by the through the waveform reconstruction. Okay, so again the digital form of the signal will be reconstructed as a shape of the applied input signal. Okay, so here we can have some analysis of the obtained digital form of the signal, and but after that analysis we can apply to the waveform reconstruction, and from that it will be applied to the vertical amplifier. Okay, this is the basic digital storage oscilloscope plot diagram. So here the digital oscilloscope digitizes and stores the input signal. Okay. First of all, it stores the first converts into digital form, and after that it will be stores. Okay, and this can be done by the use of CRT and a digital memory. So to display the signal or to construct the digital storage oscilloscope, we require a CRT and a digital memory. Okay. So first of all, digitization is nothing but the conversion of the input signals into samples. Okay. So the maximum frequency of the signal, which is measured by the digital oscilloscope, depends on the two factors. The maximum frequency of the signal, which can be measured by the oscilloscope, depends on two factors. That is sampling rate and nature of converter. Sampling rate and nature of converter. So how we can reconstruct the signal, how we can consider the reconstruct the signal, that we will see. Okay, so the first one is sampling rate. So for a safe analysis of input signal, the sampling theory is used. So I think you may familiar with the sampling theory. Okay, sampling theory states that the sampling rate of the signal must be twice as fast as the highest frequency of the input signal. So the sampling rate is the must be as twice 2 FM. Okay, so 2 FM, fast as the highest frequency, that is the maximum frequency is the FM, and for that it is twice, so 2 FM. Okay, for the requirement of high sampling rate, the digitizer is an analog to digital converter having high fast conversion rate. So here, to produce the high sampling rate, we have to use the high fast conversion rate A to D converters. So here we have number of A to D converters, ADCs. So out of that we have a flash ADC. Flash ADC is the having the fast conversion rate. Has high fast conversion rate. So this ADC converter, flash ADC converter, will produce this fast conversion rate. But the construction of the using of this ADC is the expensive. Okay, because the number of op-amps so which are used in the ADC is the increases, and due to that the cost of the flash ADC will be increases. Okay, so that's why by using this ADC, so flash ADC, which results resolution decreases with increase of the sampling rate, and because of the sampling rate, the bandwidth and the resolution of the oscilloscope are limited by the ADC. Okay, by using the ADC, so we have a limited operation, that is the limited bandwidth, and resolution of the oscilloscope is also limited because of the use of ADCs, flash ADC. Okay, so this will be disadvantage is, so the limiting of the bandwidth and the bandwidth and the resolution will be overcome by using a shift registers. So the need of the analog to digital signal converters can also be overcome by using the shift register. Okay, so by using the shift register, we can overcome that problem. Okay, so in the shift registers, we can store the digital form of digital signals in the shift registers. For the memory purpose, we can use these shift registers only. The input signal is sampled and stored in the shift register. The in this case, we are not use the ADCs. We just convert the samples, and those samples will be stored in the shift register. We cannot use the these ADCs. Okay, so samples will be obtained. Okay, and those samples will be stored in the shift register. From the shift register, the signal is slowly read out and stored in the digital form. This method reduces the cost of the converters and operates up to 100 mega samples per second. So using this shift registers, we can reduce the cost of the converters. Okay, and we can operate at 100 mega samples per second. Okay, so the only disadvantage of the digital oscilloscope is that it does not accept the data during digitization. So while performing the digitization of the input signal, so in such situation, it does not accept the data, and in such situation we have a blind spot at the time. So just we can get the blind spot. We had a blind spot at the time. So this, while the digitization process is doing, it does not respond for the input signal. In such situation, on the CRT screen, we will have a blind spot is produces. So that is only the disadvantage. That is only the disadvantage of the digital storage oscilloscope. So while performing the digitization, so it does not respond for the input data, or it does not accept the input data. After performance of the digitization, it will receive the data. Okay. So here we are saying that two operations. One is conversion of the analog digital to analog to digital form, and that will be stored in the memory. After storing the memory, data is stored in the memory. Again, we have to reconstruct the data which is applying for the CRTs. Okay, so how we can reconstruct the waveform? Okay. So for visualizing the final wave, the oscilloscopes use the technique of interpolation. Okay, so I will show you a figure. So here we have so these are the dots, like samples we have. Okay, so this is the representation of the waveform without interpolation. Okay, so to clearly identify the signals, so with these dots we cannot understand how the waveform is producing on the screen. So for that we have to reconstruct the signal. For that reconstruction signal, we are using two types of interpolation. So linear interpolation and sinusoidal interpolation. So these two interpolation techniques are using in oscilloscopes. Okay, two interpolation techniques will be used. By using these two techniques, we can reconstruct the actual signal which is applied at the input. Okay, and from the memory we will apply to the vertical deflection plates. Okay, while applying on the vertical deflection plates, the display will be like this, just like dots. So we do not get any real form of the signal. So to use the real signals, so we have to use the interpolation technique. So those interpolation techniques in the CROs, we are using two techniques, that is linear interpolation and another one is the sinusoidal interpolation. So by using linear techniques, we can we will connect the dots. By a lines. In a linear interpolation, we will connect the dots using a straight lines. Okay, so this straight lines will we will obtain some shape of the waveform. Okay, and similarly for sinusoidal interpolation, we will produce this sinusoidal waveform. Okay, so by using linear interpolation, we can construct the pulse and square outputs. By using this linear interpolation technique, we can reconstruct the square and pulse signals. But we can obtain the sinusoidal waveform. Using the sinusoidal interpolation, we cannot produce the pulse and square outputs. By using linear interpolation, we can produce the square and pulse signals. Okay, so by using sinusoidal interpolation, we cannot produce the square and pulse waveforms. Okay, so using sinusoidal interpolation, we can only produce the sinusoidal signal. By using linear interpolation, we can also produce the pulse and square outputs. So this is like a triangle, like a linear ramp signals. Okay, so increasing and decreasing, or we can consider it as a triangle shape. Okay, so by using this method, we can also produce the pulse and square outputs. Okay, with this method, we cannot produce the sinusoidal signal by using linear interpolation. By using sinusoidal interpolation, we can produce only sinusoidal signals. So that is explained here. So figure B shows the linear interpolation. It is like a straight lines used to connect the dots together. So this will work well for creating the pulse and square waveforms. So whereas figure C shows sinusoidal interpolation gives much better fit for sine waves. For sine waves, it will provide better representation. Okay, and not suitable for pulse and square waves. So this is the actual block diagram of the digital storage oscilloscope. Previous one is the basic digital storage oscilloscope, basic one. So this is the block diagram of the digital storage oscilloscope. So here we have input, okay, and input attenuator. So it will decrease as the input signal, okay, and that signal is applied to the vertical amplifier. So vertical amplifier will be amplifies the applied input signal, and that signal is analog form of the signal, and the analog form of the signals will be converted into the digital form. So for that we have some sample and hold circuits, and through that it will be applied to the analog to digital converters. In the analog to digital converter, the output is in the form of digital form that we consider as a data. Digital form, it will be considered as a data, and that data will be applied as applied to the memory to store. Okay, so for the memory, so we have to give the signals, read and write signals. Okay, read and write signals depending upon the when it is write signal is applied, the data will be write in the memory. When the read signal is applied, the data will be obtained from the memory. Okay, the data will be put out from the memory, and that data will be given to DTA converters. And the input signal from the vertical amplifier is applied to control logic through trigger circuit. Okay, and from this control logic, it will generate the control signals. So what function is to be performed? Okay, so according to these control signals, the conversion of the A to D converter and read and write of the memory will be performed by using these control signals. Okay, so by using, okay, and so the data which is out, it means when the read signal is applied to memory, the memory will be put out the data on the data lines. Okay, those data lines will be applied to DA converters. Similarly, the vertical amplifier signal is also produced as a from the vertical amplifier signal, the signal will be applied to control logic, and from that it will be applied to horizontal. So it is also in the form of digital form. Okay, so actually from the trigger circuit we will get the sawtooth waveform actually in the normal CRO. Okay, those signals will be also converted into the digital form by using this control logic, and that signal is applied to DA converter. and the DTA converter will convert the both the vertical signals and the horizontal signals into corresponding analog form of the signals, and those analog signals are amplified by using vertical amplifier, vertical deflection amplifier, and horizontal deflection amplifier. So here the vertical amplifier and the horizontal deflection amplifiers are used to drive these deflection plates. Okay, so to drive sufficient voltage to be applied. Okay, to apply that sufficient voltage, we have to increase the strength of the signals. Okay, for that, the after conversion of the digital data into the analog form, and that analog form of the signals will be amplified, and it will be applied to the, here it is vertical deflection plates, and from the horizontal side the converted analog signal will be amplified by using horizontal deflection amplifier, and it will be applied to the horizontal deflection plates. So like this, it will produces the signal. Okay, here we are converting into the analog form. So in the previous basic digital oscilloscope, we are using some reconstruction of the waveform by using interpolation techniques. So here there is no interpolation techniques. We are converting the digital signals into analog form, and those analog signals are amplifying and applies to directly deflecting plates. So here the main purpose is the applied signal, whatever the input signal that is applied to a CRO, that should be converts into digital form, and it will be stored in the memory, because this is a digital storage oscilloscope. So we are storing the applied input signal in the form of digital. So that's why, so that storage of the data is in the form of digital, and that's why we require some memory devices. And when we require to display the actual signals, or again we have to analyze. Suppose we are stored the signal, after some time I have to analyze the waveform. In such situation, again we will retrieve the data from the memory, and that retrieved data will be applied to the deflection plates through again digital to analog converters. Okay, so like this we can have the benefit of the digital storage oscilloscope. So the digital storage oscilloscopes can be available in processing and non-processing types. So previous this diagram will shows the only single channel or single input. Okay, single input. So for the next thing, so this is the another digital storage oscilloscope. So in this case we have 4 inputs. In this case we have 4 inputs 1, 2, 3 and 4, and for each inputs we have attenuate and offsets, and after that we can again amplify the signal, and it will be converted to the digital form by using 10-bit ADC. 10-bit ADC. So similarly for each signals we have this same construction. So amplifier, attenuator and offset, and 10-bit ADC. Okay. So after the input signals are converted into digital form, and those information is stored in the memory. So 1024 word memory. So like this we have four sections, memory sections. Okay, and like that we can suppose we have to use the single input only, single section only, then we can able to store the entire memory. So we can use the entire memory for single signal. Suppose the applied signal having having a number of input signals. Okay, so then the entire memory signal is used for storage of the single input. If we are using two input signals, in such situation we can go for storage of the these two input signals with the two memory sections. Okay, these two memory sections we can use for storage of two input signals, and other two input signals are used for store in the remaining two memory sections. So like this we have, if we are using four input signals, different input signals, then so each input signal is stored in each single word memory section. Okay, 1024 words memory section. So like this we have memory sections, and after this we have record control here. So record control. So from this record controller and the trigger circuit and timing and mode logic. So with this we can present the output which is stored in the memory, so that the data which is stored in the memory can be placed at the output section. Okay, output side. So that is here again we have an output control. Okay, this output control, from this output control we can able to access any data in any section. Okay, according to that the output control will be place the signals or the data which is stored in the digital form will be placed at the output side of the this output control, and that signal is applied to the 12-bit DAC or 10-bit DAC, and actually this is 10-bit DAC. This is also 10-bit DAC. Okay, so after that it will be converted into the digital to analog form, and that converted analog signals we are applied to the deflection plates of the CRO. Deflection plates of the CRO. So like this we have. So here this is the record controller. So record controller have the control over the recording of the converted digital signals. Okay, and which signal is to be placed in which section. That if the applied signals are only two applied signals are applied, and then how we can store the data in which memory sections. Like that, control of the recording will be done by this record control. So output controller is used for to take the data from the different memory sections. So record control is nothing but the writing controller, and output control is nothing but the reading controller. So generally we can say output means we are retrieving the data, digital data from the different memory sections, and that data will be sent to the two DACs. So one is for the vertical section, and another is for the horizontal section. So these DDA converters will convert the digital form of the memory signals into the analog form, and those are applied for the vertical and deflection plates of the CRO. So like this we can use the digital storage oscilloscope, a number of signals. Here we can use the 4 signals at a time. So the main benefit of this type of the signals, this type of the storage oscilloscopes are, so we can get the digital output. We can obtain the digital form of the output. So what is the signal we are displaying on the CRT? Okay, that signal can be read out in the digital form. We can display on the 7-segment display. So the data which is retrieving, suppose I have to retrieve the data in the this first memory section, and that is applying to the vertical amplifier of the CRO, and we are getting the output here. Okay, that same data will be used for the digital display. We can display in the digital form, so that is a 7-segment display. Okay, so like that we can use the further readout purposes. And one more thing is that, so we can also from this digital data, so and we are converting into the analog form. So after converting into the analog form we have to we can print the signal. So we can print the signal. So by using the recorders, okay, by using the recorders we can take the printout of the actual signal. So that is also possible by using this digital storage oscilloscope. we can take the printout of the actual output form in the hard copy. Okay, so in the CRO you can get the visualization. So by using a printer, by taking the printout of the actual signal, so we can get the hard copy of the signal. That is possible. That is possible with the digital storage oscilloscope. And there is a provision that so we can display the two signals on the same screen. So we can display the two signals in the same screen at a time. And with that we can compare the different signals, frequencies and voltages. Okay, so these are the some benefits of the digital storage oscilloscope. So, and one more thing, in the we can easily change the signal. So suppose while for first I was applied a signal and that is stored in the memory. Okay, so we can erase the signal easily, and we can use the display of the another signal. Okay, so that is also we can do easily using this digital storage oscilloscope. So the voltage and time scales of display are easily changed after the waveform has been recorded. Okay, so which allows expansion of the selected portions to observe greater details. Suppose we because the signal is already recorded, so there is no need to apply again and again. Okay, once the signal is displayed, so we can observe the different parts of the signal. Okay, so that one is called as magnification. Magnification. Some sort of the signal, some part of the signal, we can produce the output. Okay, we can take that particular portion, and that portion of the signal will be displayed on the CRT screen, and we can observe that particular portion only. Some complex waveforms will have different variations at the same time and the same amplitude. Okay, so for such signals we can observe how this striking type of the waveforms are generated. So those should be easily identify, and we can observe the or analysis that particular signals. So what happens if suppose the signal is generated, in such a way కాసేపాగం suppose we have a waveform like so like this. So we have to observe the waveform at this particular portion. Okay, so this particular portion will be observed by using magnification process. Only this particular portion will be displayed. Okay, by that we can analyze that particular signals. Okay, at that time of the at that particular time, what happens? Okay, what happens? So in heavy machines in industries, we have so in heavy machines that those are will be rotates, so it will produce some sort of sounds, and due to that vibration it will produce sounds. So when we have to record that vibration of those sounds, from that vibration sounds we can analyze the operation of that particular machine. Okay, suppose there is some problem is there, or some obstructions or something is there, the machine will produces some different sort of sounds. Okay, so sharp rise and sharp decrease like this. Okay, so to analyze these signals, so we have to first observe this, how it was happened like this. So if there is any effect on the further units of the machinery, so that we can understand by using observing these particular waveforms. So that will be also easily observed using this particular digital storage oscilloscopes. Okay, so that is one of the major benefit of using digital storage oscilloscope, because the signals are stored in the memory. So at any time we can retrieve. Okay, after suppose this situation is happened in the night duty, so when you are went to in the morning, so you have to observe that particular information. So what happens in the night situation, so that we can easily display and we can analyze. So like this we have more benefits using the digital storage oscilloscope. So one more thing, that is for the digital storage oscilloscope we will use only normal CRT. Okay, so ordinary CRT we cannot use the storage type of the CRT. In the storage CRT, storage oscilloscope, we are using different CRT. So we have flood guns, all those things. So that type of the CRT we are not used in digital storage oscilloscope. In the digital storage oscilloscope, we will use the normal or ordinary CRT. So just like electron gun, deflection plates. Okay, so that's structure only. So we can also have a cursor in that CRT screen. We have a cursor, and with that cursor we can identify the voltage and time values displayed on the digital on the screen. Okay, so by placing that cursor on the particular portion of the signal, we will get the what is the time on and what is the amplitude of at that waveform. So that is one of the advantages. Suppose we have a waveform like this. Suppose we have a cursor here. So here we have a cursor. So when we place this cursor here, so that particular at that particular point